Unijunction transistor. Here aluminum rod is alloyed to silicon slab. This silicon slab is lightly doped. This aluminum rod is acting like an emitter, and this end of the silicon slab we will call as B2 and this end we will call as B1. This is ohmic contacts. This is also ohmic contact. The resistivity of this is high because it is lightly doped. The resistance between this base 2 and base 1 here onwards we will call as interbase resistance. Okay. The resistivity offered by upper part of this layer will call as RB2. Resistivity offered by the lower part of this layer will call as RB1. This resistivity offered by this lower part RB2. Okay. So here you can see this is also another way to show UJT emitter base 2 base 1. This is equivalent diagrams. The resistivity offered by this part I will show as RB2 and this lower layer I will call as RB1. Wherever p-type silicon rod is connected to p-type aluminum rod is connected to silicon slab, n-type silicon slab, wherever aluminum rod is connected to silicon slab, this aluminum rod is acting like a p-type material. That's the reason it is acting like a p-n junction diode. So wherever this rod is joined to this slab, that part where a junction is formed, that junction we have shown using this diode. The barrier potential of this diode is 0.5, in and around 0.5 volts. This is an equivalent diagrams of UJT. The lower resistance or resistance offered by the lower layer we have shown as a variable because if you connect a power supply to emitter and base 1 and if you forward bias this diode, means if I am connecting a power supply here as I shown here, I will show you here, so I will just show you using this marker. Okay, assume that I am connecting a power supply here. Okay, assume that we should give a power supply here also. Assume that I am connected a power supply of 10 volts. 10 volts and I'm connecting some variable power supply here. Okay, when you give enough supply here so that if you are forward biasing this diode, the current will passes like this, means current will pass from this emitter to this region. This is a p-type material, aluminum, so hole is injected to this lower part of the slabs. Resistivity of this lower part will reduces and conductivity of this will increase. Listen here, this is a silicon slab. When more and more holes are emitted to this part, the carrier concentration increases, or else I can say that conductivity increases and resistivity of this part, especially this part, will reduces. Okay, that's the reason this RB1 is shown as variable. In the absence of this emitter current, when this emitter current is 0, means if this diode is not forward biased, there is no possibility of the current flowing to this lower layer. So this RB1 is very high, is like in terms of 5 kilo ohm and 5 kilo ohm or 8 kilo ohm, or it is in terms of kilo ohms. When you if you are able to give enough supply here, and if you are able to forward bias this diode, so carriers are injected to this layer, carrier is injected to this layers, so resistivity of this layer will reduces, conductivity will increases, so resistance of this resistance will reduces to value like 50 ohms. So that's why I have shown this as a variable resistance. Okay, now the next question is, we have understood that the resistivity of this part is variable based upon the emitter current. So how much voltage is required to forward bias this diode? Listen here, I will give you some values 10, and I will take you some 2 kilo ohm, this value 2 kilo ohm, and I will take 8 kilo ohm, this I will take as 8 kilo ohm. Can you give me what is the voltage drop here when the emitter current here is 0? When the emitter current here is 0, assume that this is not forward biased. So my question is, how much voltage I should apply here to forward bias this? Because if you apply Kirchhoff's law, we can see here this voltage applied in between these two should be more than this barrier potential and this drop to overcome to forward bias this diode. Means anode to cathode should be more than 0.7 only when this is equal to more than 0.5 plus this drop. What is the drop across this resistance? See here, if you see a current which is flowing in this path is 10 volt divided by 2k plus 10 volt divided by 2k plus 8k, that is 2k plus 8k so that is 2k, how much it is? 10 cancel, k 1 milliamps of current is flowing, and 8k into voltage drop across this resistance is 8k into 10 divided by 2k plus 8k. How much that is? 10 cancel each other, so k goes to here, milli, k cancel with milli, so 8 volts. So voltage drop across this is 8 volts. If you consider this is 0.5, so when this applied voltage is more than 8 plus 0.5, then only this forward bias. When the applied voltage is more than 8.5 volt, then this is forward bias. Until that, this is not forward bias. If you are applying a more than 8.5 for this case, this current means this is forward biased, means from these material holes are injected here, the resistivity will reduces. This resistance from 8k it will come to like 50 ohm or very small ohms. So resistivity of this will reduce. This is a characteristic of UJT. This is what here shown. See, we are doing an experiment. We are connecting a supply like this, and I'm applying varying variable voltage here, and we are measuring emitter voltage, means voltage in between emitter and base 1 and emitter current. And if you are connecting a emitter here, uh, current meter, what is a value it shows you, that's value. So then that is an emitter current. Now, so we'll do an experiments. So we are varying a voltage from 0. We are plotting here emitter voltage here, and emitter current here. See, assume that we are connecting one voltmeter here, voltmeter here, one voltmeter. So for measuring emitter voltage, and one current meter here. Okay, so whatever this voltmeter value is emitter voltage, and this is a current meter value is emitter current, and we are plotting that. So emitter, so initially when you start apply emitter voltage is 0 or like that, there is no current is flowing here, so that's the reason emitter current is 0. But as usual, diode whenever it is not forward biased, but still reverse minority current flows. So whatever current here it is shown, so this is a minority current, so it is almost like this, minority current will flow. So you just believe on this red line now instead of this is more appropriate. So this small minority current, reverse minority current is flowing. It is there purely because of minority carrier flow. That will continue. So assume that I am applying 1 volts, 2 volts, 3 volts. We have explained, no, it is not enough to forward bias this diode. So only minority carrier current flows. Whenever the applied voltage somewhere here, assume that it is like 8.5 here. We are applying for this setup. I said it is 8.5. If it is 8.5, so at that time, okay, here I will call this as a V peak, okay, V peak, because at that time UJT will turn on. So what happens? Current starts increasing, current starts increasing, current starts increasing. As I told earlier, here one good behavior is the current starts increasing. As soon as current starts flowing to this layer, to this lower layer, resistivity will reduces. That's the reason this region is called as a negative resistance region. So from 8K, the resistance will come down till around 50 ohm or like that value. Okay, so that's the reason resistance will come down. Okay, so but current will increase, current increases, current increases, current increases. So how, till what value resistance will come down? Resistance will not reach to 0, resistance will reach to like 50 ohms or something. Okay, later on, even if current comes to this, or if any higher current comes also, the resistance will not change, resistance will not change. Means we have reached to valley point, we have valley point. Okay, later if you are applying more and more voltage to this emitter base 1 terminal, what happens? Current will increase. This is just like a diode forward characteristics, current will increase. The resistance of this layer here onwards will remain constant, That's the reason it is a saturation region. Resistance will not, resistance as saturated, in the sense it will not reduce here onwards. This point is called as valley point. Okay, the corresponding voltage is VB. See, corresponding voltage is very less compared to VP. Why? Because here this resistance is very small, this resistance. So this is a VB and this is V peak. The corresponding current here is IB and corresponding current here is I peak. So this is a characteristic of UJT. This we are using next slides. Okay. So we'll read out this whatever explained here so far. UJT has 3 terminals called as the emitter, base 1 and base 2. Between base 1 and base 2, the unijunction has the characteristic of ordinary resistance. This resistance is the interbase resistance RBB. Entry base resistance RBB values in the range of few ohms to kilo ohm. A slab of lightly doped N-type silicon material has two contacts attached to both ends of one surface. An aluminium rod alloyed to opposite surface. The PN junction of the device is formed at the boundary of the aluminium rod and the N-type silicon slab. The aluminium rod is alloyed to the silicon slab at a point closer to base 2 contact than the base 1 contact. The base 2 terminal is made positive with respect to base 1 terminal by VBB volts. The circuit equivalents of UJT consist of two resistors, one fixed, one variable, and single diode. The resistance RB1 is a variable resistance since its magnitude will vary with current I. In fact, for a representative unijunction transistor, RB1 may vary from 5 kilo ohm down to 50 ohm for a corresponding change of I from 0 to 50 microamps. See here, I, if you are at 0, the RB1 is 5 kilo ohm. If you are increasing to 50 microamps, RB1 will change to 50 ohms. That's the reason we are representing using a variable resistance. The interbase resistance RBB is a resistance of the device between RB1 and B2. RBB is RB1 plus RB2. So this character of this UJT we are using to design a relaxation oscillator circuit. Okay, this is a relaxation oscillator circuit. Here a resistor is connected here, capacitor is connected here, RC circuit it is, and the supply we have shown here. You can call this as a VS here onwards, VS. Okay. So when the DC supply Vs is applied, the capacitor C is charged through resistor R because the emitter circuit of UJT is in open state. What we are saying, when you're connecting a supply like this, the capacitor will charge. Why capacitor will charge like this? Because current won't flow here because UJT is not on now. This diode, whatever earlier I have shown, this rod wherever this slab is interconnected, no, where there is a one diode, that diode is reverse bias. So the capacitor is charging through resistor R and R. Okay, how fast capacitor will charge depending on the values of R. Okay, forget that, we will decide later. Now, so capacitor will charge. How long capacitor will charge? Capacitor will charge as I have shown here till capacitor charges the voltage whatever is available across the capacitor reaches to value V peak. So previously I have shown, once the applied voltage to emitter is equal to V peak, what happens? More and more carriers are injected to this lower layer, this resistance will come down. That's the reason what happens, this resistance will come down to very small, like 50 ohms. So it is here onwards I will say that UJT is turned on. So what happens, the current capacitor will discharge in this way as soon as UJT turns on. When UJT will turn on? When the capacitor voltage reaches to V peak. So here I have shown the charging cycle of capacitor, because charging happens through this resistor R, charging time is more because this resistance value is very high, and discharging happens through the capacitor and this UJT base. This UJT resistance is very small because UJT is already turned on. The discharging time is very small. Okay, now this capacitor will discharge. How long? It will discharge until it reaches to value VV. Once it reaches to VV, what happens? Or if it is trying to come below VV, what happens? So as I told earlier I told you, this can reduce. This is having a minimum value like 50 ohm. So if it is having 50 ohm into current which is passing through that is a drop across this, and this diode draw 0.5. So if you are saying that it is something around 2.5, so 2.5 and plus 0.5, that is 3. Okay, I will show you actual value. If I'll consider it as 50 ohm, what happens? 10 divided by 2k plus 50 ohm, how much it is? 2.05 k, yeah, 2.05 k, that is a current flowing here, into 50 ohm, that is a drop here, this 0 cancel with this 0, this 10 divided by it is 50 divided by 2 is how much? 2.05, I will consider as 2. 50 divided by 2 is how much? Can you give me an exact value? 50 divided by 2.05. 50 divided by 2.05. 50 divided by 2.05, that is 24.39. I can in 24.39. okay, 24 that is 50 divided by 2 into milli 24 millivolt. Yeah, 50 divided by 2.05, it is 24.3. so 24 milli volt. I will give you values. 50 ohm, then that is value. 10 divided by 2k to 50, not this, this is 500 divided by 2.05, 500 divided by 2.05, that is 243 into k. 500 divided by 2.05, that is 243 k means milli, 243 milli means 0.2. okay, 0.2, so it has a 1.7 now. okay, so if you consider that is this is a VV, this is a VV, this is a VV, so once capacitor comes below that value, capacitor voltage comes below VV, what happens? This diode will turn off, this diode will turn off, because to work to forward bias this diode 0.5 and this VV, this capacitor voltage should be more than 0.5 plus VV. When the capacitor voltage is coming below 0.5 plus VB, then this diode will turn off. If this diode turns off, what happens? So there is no paths for capacitor to discharge. So once again, from this supply, capacitor will charge. So that's the reason again charging starts. So this is an oscillation. It's an oscillation. Okay, this oscillation will continue. It will charges, and here on next second cycle onwards, this capacitor will start charging from VV and it ends at VP. Again, same thing repeats. Here in this side, if you are able to tap your current or voltage, whatever it is coming here, you can see here this RB1. Assume that we are connecting one resistance here, and I am observing a voltage somewhere here. What happens? The voltage is available only during discharging, because correct, only during while capacitor is discharging, only during when UJT is on. That's the reason. So if you call this as a VB1, if you call this as a VB1, so VB1 is available only during discharging, and this discharging we are choosing very small resistance here. Sometimes we are choosing a pulse transformer here, for tapping the voltage, and this resistance is very small. That's the reason discharging is very short, discharging time is very short. Okay, so this pulse whatever we are generated here, we are using to fire the SCR. We are connecting this to the gate of an SCR. Okay, so this pulse position is determined, or it is determined by the values of R and C. If you are fixing C and by varying R, this pulse position I can vary, means how much time it takes to reach to V peak, that is decided by this value R. Okay, by varying R we can change the firing angle. So when the emitter voltage VE decays to value point VB, the emitter ceases to conduct, UJT turns off, and charging cycle repeated. This is explained. The time constant of charging circuit T is equal to RC. This is RC. This triggering voltage should be sufficiently large to turn on SCR. As I told earlier, the value of R and C will decide when exactly this triggering pulse starts. So this timings is decided by value of R and C. By varying R and C, I can fix my this timing. So we require a proper equation to fix this R, C and this T. Okay, how to derive that? See, here I have shown complete circuits where UJT, this whatever voltage I am getting here, I am connecting to SCR. So recommended range supply for it's 10 to 35 for fixed values of a peak voltage. So as I told, V peak is N VBB plus VDD, N into Vs plus VDD. VD is the diode drops, TGs are R1C. Okay. See here, as I told earlier, you may be very familiar, capacitor voltage formula is the voltage across this capacitor. What I am saying, the voltage across this capacitor. So if I am measuring like somewhere here, using plus and minus, so voltage across this capacitor is Vs 1 minus e power minus t by RC, this RC. Okay, see here, when t is 0, what is the voltage? Capacitor voltage is Vs 1 minus 1, 0, means capacitor voltage is 0 when t is equal to 0. When t is very high value, this value is reaches to nearer to 0, so capacitor voltage will reaches to Vs. That is only if this circuit is there, but here we have some other component, the behavior will change. Okay, but this is a equation rule describing the R and C circuits. Okay, I'm using this. So when exactly here I have shown capacitor will reach to V peak when exactly, when the here onwards, here to here timings I will call as tau 1, and I will say as R and C. Okay, when this is T axis and this is capacitor voltage, T here independent variable is T and the dependent variable is capacitor. When this T takes a value of tau 1, the capacitor voltage will reach to V peak. So that's the reason when capacitor voltage reaches to V peak, T reaches to tau 1. So Vs divided by V peak is Vs divided by 1 minus e power minus 2 1 divided by RC. What I am saying, when t equal to 2 1, capacitor voltage reaches to V peak. Last class, in the previous slide, we have shown that what is the formula of V peak. V peak is eta into Vs plus Vd. Or else, what is a V peak? V peak, what is a V peak? V peak means, as I told earlier, so you can see here, when exactly this equal to overcome this when V peak is Vd plus the current flowing here and resistance of this, that's all. So current which is flowing in this path is Vs divided by Rb1 plus Rb2, and the resistance of this layer is Rb1, and the diode drop is Vd. So I will write V peak, Rb1 I will write here, Rb1 plus Rb2, Vs plus Vd, and V peak. The ratio of Rb1 to Rb1 plus Rb2 I will call here onwards as eta into V eta. So this Vs by Vt. Eta here onwards I will call as intrinsic standoff ratio. Value of eta is 0.5 to 0.8, something nearer to that. Okay, so we got an equation. V peak is eta into Vs plus Vd. This value I will substitute here. So what is Vd? So one more thing, what is Vd? Vd is diode drop. It is in UJT, it is 0.5. So eta into Vs is much more than VDD. So it is only for simplification. We are neglecting the diode drop. So then V peak I can say that eta into Vs. So I will substitute in this equation, in these equations. Instead of V peak I will say eta into Vs. So eta into Vs is equal to Vs 1 minus e power minus tau 1 by Rc. So eta is equal to Vs cancelled, 1 minus e power minus tau 1 by Rc. I will rewrite this e power minus tau 1 by Rc. I will take this to left, 1 minus eta. So you take this to denominator, this is e power minus, so when it goes to denominator it comes plus 1 divided by e power tau 1 by Rc, 1 minus eta. So again 1 by 1 minus eta e power tau 1 by Rc. So you take a natural logarithm on both sides, ln 1 by 1 minus eta is equal to natural logarithm of e power t1 by tau 1 by Rc. Natural logarithm of tau 1 by Rc is equal to ln 1 by 1 minus eta. So what is a natural logarithm? This I can say tau 1 by Rc, natural logarithm of e. Natural logarithm of e is 1. So tau 1 by Rc, natural logarithm of 1 by 1 minus eta. Tau 1 Rc, natural logarithm of 1 by 1 minus eta. T is equal to tau 1 plus tau 2. So tau 1, see here one thing is we are calling this as tau 1 and this as tau 2. Here also tau 2 is very small compared to tau 1. So actual t, period of oscillation, this is a periodic waveform, period of oscillation is t. Actual t is tau 1 plus tau 2. Tau 2 you neglect, then I can it is approximation. The period of this oscillation I will consider as tau 1. So period of oscillation is I will consider as tau 1. I will neglecting tau 2. Tau 1 is much greater than tau 2. That's the reason t I will say as tau 1. So instead of tau 1 I will write t. So t becomes Rc ln 1 by 1 minus eta. This is a equation which we are using to fix the firing angle. For an example, you require firing angle at 90 degree in India, because in India 50 hertz as a supply. So 20 millisecond is a period of power supply. So first half cycle means 10 milliseconds. 90 degree means half of the half cycle, means 5 milliseconds. Means exactly after 0 crossover, after 5 milliseconds I require firing pulses. That's the reasons this t should be 5 milliseconds. So here you write 5 millisecond, you take some C value like 10 microfarad or 1 microfarad and take respective R value. You take eta by referring data sheet, maybe it is in terms of 0.5 to 0.8 depending upon what UJT you are using. Okay, so this is how we can change the firing angle of UJT based UJT relaxation oscillator based firing circuit. This is one firing circuit in analog days widely used to fire the SAR. So next we need to learn a little deeper into this. So how to choose this R? As I told, this is a fixed one formula. Okay, then one precautions we need to take. See, if you take R very smaller value or very bigger value, what happens? Capacitor voltage, if you take very higher values of R, the current which is flowing in this path is very small, so it may take more time to charge this capacitor, so that capacitor voltage may fail to reach V peak within requirement in this case. So that is a point here. So capacitor value resistance value should not be too big, and again it should not be too small. If it is too small, what happens? See, a capacitor voltage should come below VV, then only you can see here UJT will turn off, correct? So one thing is, capacitor voltage should reach to V peak and it should come below VV also. That's the reason wisely we should choose R. So what is the condition for that? See, assume that right now you assume that UJT is in off. When capacitor is charged, so voltage across this capacitor should be equal to V peak, correct? Should be equal to V peak. So what is the voltage across this capacitor? That is Vs minus current into this resistance. Vs minus current into this resistance should be greater than V peak, then only UJT will turn on. So once you can see when the voltage across this capacitor is just below V peak, the current flowing is in this. As soon as it reaches to V peak, the UJT will turn on, current starts flowing in this path. Now I can say that whatever current which is flowing in emitter is same as the current which is flowing in a resistor. That's the reasons at that instant I'm saying that whatever actually you can see here, whatever current, when the emitter voltage is V peak, the current flowing to the emitter is I peak. So current flowing to the emitter is I peak. It is coming from this resistor. That's the reason the current through that resistor I will consider as I peak. So Vs minus I peak into R should be greater than V peak, and if I rearrange this, Vs minus Vp should be more than IPRP, Ip into R, IPR into R should be less than Vs minus V peak. So R should be greater than Vs minus V peak by I peak. Correct? No, R should be lesser than Vs minus V peak divided by I peak. So then next, as I told earlier, R should not be too small. So when the capacitor voltage comes below VV, then UJT should turn off. So this R should allow such a situation. For that reasons, so exactly when capacitor voltage is equal to VV, so what is the capacitor voltage formula? Vs, this is Vs minus current into R. Vs minus current into R should be less than VV, then only UJT will turn off. So as soon as UJT turns off, what happens? Current whatever is coming here, it will start flowing in this direction. So what I'm saying, till at that instant means when exactly the voltage across this is VV, the current was flowing here was IV. So thereof just after that, in that transition time, the current which is moving to capacitor I will consider as IV only. So it is coming from this, so I will choose IVR should be less than VB. So VS minus VB should be less than IVR should be greater than Vs minus Vb, or should be greater than Vs minus Vb divided by IV. So this is a condition. What it says that R should be greater than this, and R should be less than this. R should be less than Vs minus V peak by IP, and R should be greater than Vs minus Vb by IV. The recommended range of supply voltage is 10 to 35. See, as I told here, the width of this is very small. The width of the triggering pulse is R1 into C. See here onwards, for tapping the this voltage, I require one. I will connect one resistance. If you call this as an R1, then this interbase resistance I will consider as very small. So the this width is entirely depend on this R and this C. So TG is R1C. Resistor R2 is generally connected here. Resistance, one more resistance I will connect it here R2. Okay, so this is to compensate the temperature effect. Means what happens, as I told here, there, V peak formula is eta into Vs plus Vd. So when exactly this firing pulse will generate is depending upon V peak, means when exactly capacitor voltage will exceed this, but this V peak is depending on temperature also, because this Vd will change when temperature changes. So Vd will reduce when temperature increases. So some mechanism is required to overcome this problem caused by the temperature, thermal runaway. This problem is called as thermal runaway. So what we do here, we'll connect one resistance here. You may be knowing the resistance behavior is when temperature increases, its resistance also increases. So here the Vp is as I told earlier, eta into Vs plus Vd. Yeah, Vd may decrease because of temperature, but what happens, yeah, this whatever this resistance value increases, so drop across this also will so what happens means current which is flowing here, whatever current which is flowing to this part will little bit reduces. So what happens, as I told earlier, the interbase resistance of base 2 and base 1 is depending upon the how many carriers are flowing here, so it will reduce. So once it reduces, the interbase resistance, when the current will reduces, interbase resistance will increases. So what happens, this part because of temperature will reduces, that is compensated by eta, because RB1 will increase little bit, so this part will little bit increases. How much it has decreased, nearer to that value, here this part will increase, so that Vp will remain constant irrespective of the temperature. This is a methods to avoid thermal runaway. The empirical formula to choose Rb2 is 10 to the power of 4 divided by eta into Vs, and R1 always we are limited to values 2k or 3k are possible in some applications, always less than that very small value we are choosing for R1. Most of the times instead of R1 we are using pulse transformer. If you are using a pulse transformer, two firing pulses we can generate here from the upper primary, upper secondary and lower secondary. Thank you.